we come to the next part of the discussion of solid state, unit cell and crystal systems. Now, if you see crystal lattice, now right word which have been often used in inorganic chemistry before, lattice is nothing but a regular arrangement of atoms, ions, molecules inside a crystalline solid. So, either it can be an atom or it can be an ion or it can be a molecule. But remember, a systematic or regular arrangement is called as a crystal lattice. Basically, a crystal lattice, when somebody says the word, it's an entire structure. It's more properly called as entire structure. If you say, it's called as space lattice, a more specific word. So, if you check this arrangement that you are able to see, you are going to get the entire solid state system. So, this what you are able to see or is getting built up is called as space lattice. And if you go back, and the first thing which was a building block, that is called as a unit cell. So, first part. So, each building block then add up, go on adding up to get a huge structure. Such a huge regular arrangement of the structure is called as space lattice. Smallest part of this lattice, which can be repeated in all direction to generate entire lattice, is called as a unit cell. So, whatever has been colored is nothing but unit cell. So, if you want to imagine what is a unit cell, you can imagine a brick. A brick is a unit cell, a brick, many bricks. Now, it is irregular in this case. Imagine regular bricks. All these regular bricks, it looks irregular here. Actually, they are all regular bricks only. Bricks are all of the same sizes. Imagining all the bricks are of the same sizes, if they make up, then whatever wall is there, that wall is called as space lattice. So, what is space lattice? Wall. And what is brick called as? Brick is called as unit cell. So, brick is called as unit cell. So, wall of the house is called as space lattice, and the smallest unit which is making up brick is called as unit cell. So, remember brick as unit cell, and remember wall as space lattice. This is how you can correlate and remember this part. We go to next. Various lattice can be formed by varying this parameters of A, B, C. What is an A? A is you can imagine A and B as a length and breadth, and C as a height. We call them as a edge lengths. And interfacial angles. Are you able to see interfacial angles there? So, this angle is alpha, this angle is beta, this angle is gamma. So, we take the farthest point, generally not compulsory, we take the farthest point that is away from an observer, that point is taken, and the angle which is made anti-clockwise. First angle is alpha, other anti-clockwise is beta, next is called as gamma. These are called as interfacial angles. And the length parameters, length, breadth, height, are called as A, B, C. Location of atoms or ions with respect to each other, by varying first two parameters, we get 7 types of unit cell called as crystal system. So, crystal system has a variation in edge length and interfacial angles. What you are able to see on the diagram is cubic system. Cubic system, how to visualize cubic system? Imagine base as a square, base as a square, base. Imagine base as a square, imagine base as a square, and imagine the side also as a square, side also as a square. This is how you can remember. So, base is a square, side is also square. When you say square, all the lengths are equal and all the angles are 90 degrees. Now, do you know any such cubic system around us that you are familiar with? Yes, Rubik's cube, where all the lengths are equal and all the angles are 90 degrees and equal. The next one, tetragonal. Now, how to visualize tetragonal? If you want to design, Cubic, we remembered base as a square and side also as a square. Here you should remember base as a square and side as a rectangle. Side as a rectangle. Are you able to see in the diagram? Base as a square, side as a rectangle. When somebody says base is a square, then the base parameters A and B are equal, but the height parameter is unequal because you considered side as a rectangle. But whether it is a square, whether it is a square or whether it is a rectangle, we are all aware from our lower level geometry, angles are always 90 degree. Any tetragonal that you can remember in our day to day life? Not very good example, but this pillar, the pillar that makes up our building, right? These pillars are tetragonal, their base is square and the height wise here rectangle. Orthorhombic. Now orthorhombic, how to remember orthorhombic? Base as a rectangle, side as a rectangle is called as orthorhombic. Orthorhombic, when you say base as a rectangle, side as a rectangle, naturally for rectangle lengths are always unequal, but you know from geometry the angles are 90 degrees. Example in a real life orthorhombic is matchbox. If you know matchbox, you can see its matchbox base is rectangle, height wise or side wise is also rectangle. Orthorhombic. Right, among these three, which is the most symmetrical one? The most symmetrical one is cubic, because all the lengths are equal, all the angles are also equal. We go to the next one, trigonal rhombohedral. How to remember trigonal rhombohedral? Side as rhombus, base as rhombus. That means you will imagine base as rhombus and side also as rhombus. When you say rhombus, lengths are always equal. Angles are also equal, but they are not equal to 90 degrees, because moment they become 90 degree, then it is not called as rhombus, it will be called as square. Rhombohedral is also got the name as trigonal. So I have shown rhombus, simple rhombus, right. So imagine rhombus as a base, imagine rhombus as a side. The next, hexagonal. In hexagonal, base is a hexagon, base is a hexagon. Okay, remember that. Only base as a hexagon can be remembered. So when you say base is a hexagon, the two A and B are equal, but C is unequal. Angle in the base are 90 degrees and one of the angle is 120 degrees. So if you know this angle is 90 degree. Okay, this angle is 90 degree. Now this angle is also 90 degree, but inside angle is 120 degree. I repeat, this angle height wise is 90 degree. If you go by this angle 90 degree, inside angle can be 120 degrees. Hexagonal, day to day life, right, hexagonal can be hexagonal candles. Okay, then monoclinic. How to remember monoclinic? In monoclinic, remember right angle trapezium as a base. So what you are imagining as a base? A right angle trapezium, and side is also right angle trapezium. That means two angles are 90 degree and they are equal, but one angle, right, this is two dimensional figure, but one angle is not a 90 degree. Here, because it is trapezium, because you are imagining a trapezium, right, it is monoclinic. Remember, base as a right angled trapezium, side as a right angled trapezium. Right, for us it is very difficult to visualize here, but you can visualize two dimensionally. That's monoclinic. Then comes the next one, triclinic. Triclinic, you have to imagine trapezium as a base, side also trapezium, and everything trapezium. You know, for trapezium, lengths are always unequal, angles are also unequal in trapezium, and none of them is a 90 degrees. So if you check how many are there, 1 cubic, 2 tetragonal, 3 orthorhombic, also called as rhombic, 4 trigonal, 5 hexagonal, 6 monoclinic, 7 triclinic. So, 7 crystal systems do exist, of which most symmetrical is cubic and most unsymmetrical is triclinic. We go to the next discussion. There are 7 types of crystal system, right, of which 4 subtypes that we are going to see it ahead. So, total should be 28 if you multiply or you go by probability as a chapter. 28 possible crystal lattices are there, but in nature only half of them are existing or only 14 is existing, and this 14 lattices are called as Bravais lattices in remembrance of the great French physicist and mathematician called as Auguste Bravais. Right, so this is correctly pronounced as Bravais. He is a French, so French have their own way of pronunciation. So his name is Auguste Bravais. He is a French physicist and did lots of work in crystallography, and you know solid state is a part of a crystallography because you have a crystalline solid as a learning process. Location of an atom in unit cells. You can have like this, atoms or ions can be present as the corners of the simple cubic. Now, in reality, if you see this picture, it looks that these 2 spheres don't touch each other, these 2 spheres, but in reality they touch each other. So, this diagram is called as ball stick model. Ball stick model just gives you an idea, but this is what is a real diagram. Or these 2 spheres also touch each other, these 2 spheres also touch each other. You should know, even these 2 spheres also touch each other. Remember, these 2 are also touching each other. Right, this is one simple cubic system like this. Now, if I really want to learn this as a cube, then imagine you are cutting it like this, and you are cutting it from the front like this. You do the similar type of a cut at all other places. Are you understanding it? You do to cut, then whatever you get will be a cube with edge length as A. Are you understanding it? Now, if you want to know mathematically, this is 1/8 part of a sphere which was making up here. Are you understanding 1/8 part of it? If you can visualize. Then this system is found in all 7 crystal systems. They are called a simple cubic, or it is also called as primitive type system. Coming to the next one, body centered positions. Now, what do you mean by body centered crystal system? Body centered crystal system, that means there will be a corner and there will be a body center. What is a body center? It is at the center of the body, therefore it got the name as body centered. Such a type of crystal system is called as body centered crystal system. First type is called as simple crystal system or primitive crystal system. Second type is called as body centered crystal system. Now, this is what is a picture, and if you see that picture, and it is not so easy, but what you are able to see, they are not touching each other. That means this sphere and this sphere doesn't touches each other. Similarly, these 2 spheres also don't touch each other. There is a space, it is not seen here, but it is seen here. Are you able to see? There is no, right, it can't be there karke. So, only sphere which touches all the 8 spheres as a corner is this one. This 2 spheres touch each other, this also touch each other. I suppose you are understanding. Body centered touches all the corners, that is body centered system. This is what it looks. For your information, this is 1/8 of the sphere and this is one entire sphere inside. This is found only in cubic, tetragonal, orthorhombic. So, body centered is found only in 3 systems: cubic, tetragonal and orthorhombic. We are trying to tell you the subtypes. First one was found in all 7 systems. Second one is found only in 3 systems: cubic, tetragonal and orthorhombic. Coming to the next type. The next type is face centered system. What is a face centered system? In face centered system, you will have spheres at the corners. Yes, and spheres at the face centers. Are you able to see? I repeat again, face at the corners and the spheres at the face centers. I suppose you understand this is the behind face and this is a face center. Those who want to know, this is a face center. Those who want to know, this is a face center. Are you understanding it? I have darkened those who are face centers. Like this. This is a face center of behind, and if you want to know, this is a face center of the front face. Face centered system. It looks like this, unusual, but for your information you should know they don't touch each other. That means this two corners don't touch each other, these two corners don't touch each other, but if you want to know exactly, this face center touches the corners, this face center touches the corners, this face center touches this corner, this face center touches the corner. So, face center touches the corner. This is how it looks. Those who really want to know, this is 1/8 and this is half part of the sphere. This is found only in cubic and orthorhombic system, only in cubic and orthorhombic system. So, only in two places, right. If you remember the first one, primitive was found in all 7, body centered was found in 3, while face centered is found only in 2. End centered. Now, what is end centered? You have a corners as usual. Every system is having 8 corners. That's for sure. All of them have a corner. But in this case, you have face center only at 2 places, not at all the 6 places, and that too opposite to each other. Then such type of system is called as end centered, and this is found only in orthorhombic and monoclinic. That means it is found only in 2 crystal systems. So, if you want to know, primitive type was found in how many? All the 7. Body centered was found in 3, while face centered was found in 2 and end centered was found in 2. So, if you count all, 14 are the Bravais lattice. Primitive system is found in all 7 crystal system. Body centered is found only in 3 of those systems, while face center is found only in 2 of those systems, while end centered is found only in 2. So, if you count all the numbers, there are 14 Bravais lattice. This is what is the information. We go to next, contribution of different lattice points in cubic unit system. Now, we are trying to understand cube corner. In reality, you know, this is ball stick model, which is just for understanding. It's a model. In reality, it is like this. And if you check, this is what is a corner all about, and this corner is present in how many cubes? It is present in 8 cubes. If you clearly observe, that corner is present in 8 cubes, 4 cubes above and 4 cubes below. So, what is the contribution? There are 8 corners in the cube. Each atom at the corner is shared by 8 unit cells. So, I repeat, there are 8 unit cells for that black, or which I have made it red now. It is present in 8 unit cell. So, contribution of each corner to an unit cell is 1/8. Is 1/8. Face center. We are talking about this face center. How it looks? If you are able to see, this is a face center. Where is that face center present? Can I say it is present in this unit cell? Oh, and it is present in this unit cell also. So, it is present in both the unit cells. So, what is the contribution of this sphere to this unit cell? Its contribution is half. And what is the contribution to another unit cell? Half. So, what is the contribution of the face center? It is half. Contribution is half. Remember, any cube is made up of 8 face centers. 8. If you see, this is for behind, this is for front. Not 8, sorry, 6 face centers. Mistake from my side. 6 face centers, and each face center is a contribution of half. How many corners are there? There are 8 corners, and each corner, what is the contribution? 1/8. So, corner contribution 1/8, face contribution half. We go to next discussion, body center. For body center, this is the body center. Body center, body center. There is only one body center in the cube. So, the entire body center is present in the unit cell. So, its contribution is 1. So, entirely is present in the unit cell only. So, body center contribution is 1. Coming to the next, edge center. If you see edge center, which are shown by red color dots, edge center, if you check, then you are able to see a edge center has been shown here. It is present in this unit cell. It is present in this unit cell, it is present in this unit cell, it is present in this unit cell. So, edge center is present in 4 unit cells. That means, what is the contribution of this edge center to this unit cell? The first unit cell, its contribution will be 1/4. So, there are 12 edges and each edge is shared by 4 unit cells. The contribution is 1/4. Remember, there are 12 edges and each edge has a contribution of 1/4. Going to the next one, hexagonal corner atom. If you see hexagonal corner atom, we are talking about this hexagonal corner atom. This is hexagonal corner atom. If you see hexagonal corner atom, it is present in this hexagon. This is one. It is present also in this hexagon. It is present even in this hexagon. So, it is present in 3 hexagons below. There will be 3 hexagons above also. Remember, there will be 3 hexagons above too, similar to 3 hexagons below. So, there will be 3 hexagons above, 3 hexagons below. That means contribution of the hexagon to a unit cell will be 1/6. How many hexagonal corners are present for? How many hexagonal corners are present for a hexagonal system? If you want to know how many corners are present, the corners which are present are, how many are there? Can you count? 6 making the bottom and 6 making the face. If I want to show, there will be an hexagon here too. This is one more, and there will be hexagon here too. So, if you see, this is present in 3 hexagons below and 3 hexagons above. So, its contribution is 1/6. So, hexagonal corner atom is 1/6. So, that was lots of discussion for solid state. Request to re-see this video and understand it very well. There is lots of technical data. If you require, see it 2 to 3 times so that you understand it properly. So, we come to the end of the discussion. Thank you all. Bye.